Welcome to the first part of our chapter, oscillations. We are starting with periodic motion, a motion which repeats itself again and again after a regular interval of time is called a periodic motion. For example, motion of a planet around the sun. For example, that of Earth, which repeats itself every after 1 year or 365 days. Motion of the hands of a clock. For example, the hour hand of a clock repeats its motion after every 60 minutes. The minute hand of the clock does the same after every 60 seconds. Motion of the heartbeat, etc. All of these are periodic motion in nature. Oscillatory or harmonic motion. If a body is moving back and forth repeatedly about its mean position or a certain fixed position, then its motion is said to be oscillatory, vibratory, or harmonic in nature. For example, the motion of a pendulum, motion of the piston of an engine, motion of the strings of a guitar when plucked, etc. are the examples of the oscillatory or vibratory motion. Every oscillatory motion is periodic in nature, but remember, every periodic motion is not oscillatory. So, the motion of the pendulum of a wall clock is oscillatory as well as vibratory as well as periodic in nature. But the motion of a planet around the sun, motion of the hands of a clock, they are only periodic, but they are not vibratory in nature because they do not repeat themselves about the fixed point called the mean position of the body. Periodic function, a function which repeats its value at regular interval of time, is called a periodic function. Periodic motions can be represented mathematically with the help of the periodic function because they satisfies the characteristic property of the periodic motion that they repeat themselves at regular interval of the time. For example, the periodic function sine omega t and cos omega t, they are periodic in nature. So sine and cosine functions are periodic in nature with time period t, as it is clearly seen from the graph of the sine and the cosine function. They are not only periodic in nature, but their value also varies between maximum and the minimum value, between plus a and minus a. So they are not only periodic in nature, but they are also oscillatory because their values keep on repeating between their maximum value plus a and minus a as shown from the graph. So such kind of trigonometric functions can be used to represent the vibratory or the oscillatory motion of an object. All harmonic functions are periodic in nature, but all periodic functions are not harmonic. For example, tan, cot, secant and cosecant, they are also periodic with a time period 2 pi by omega. But because these functions, they do not repeat their values between maximum and minimum, but their values varies from 0 to infinity, so they are only periodic functions, but they do not satisfy the properties of the vibratory motion, so they cannot be used to represent the vibratory motion of any object. Simple harmonic motion. A particle is said to be executing a simple harmonic motion if it moves to and fro about a mean position under the action of a restoring force which is directly proportional to its displacement from the mean position, but it is always directed towards the mean position. So, simple harmonic motion is the motion of the particle in which it is moving about a certain fixed point called mean position under the effect of a restoring force which is always directed from its instantaneous position towards its mean position. For example, as shown in the figure, we have a block of certain mass which is connected to a spring. Other end of the spring is connected to a rigid support. So at point A, its displacement is 0. But when we apply an external force towards the right side, so that extension of the spring takes place and block of mass moves from point A to B. In this case, Under the action of external force, a restoring force will be developed inside the spring, which will be directed towards its mean position, opposite to the external applied force. So in this case, if we leave the block at the point B, the only force that will be left in the block, it will be the restoring force, which will try to bring it back toward at its mean position, that is at the point A. So in this case, the restoring force, which is directed toward the mean position of the particle, but its value is directly proportional to the amount of the displacement x suffered by the block, we call that type of motion as the simple harmonic motion. So within the elastic limit, using Hooke's law of elasticity, this restoring force is directly proportional to the displacement, that is Fr is proportional to x, or Fr is equal to minus k into x, where k is the force or the spring constant, and the negative sign is there because both restoring force and the displacement, they are opposite to each other. The spring constant is actually the amount of the force produced, restoring force produced per unit displacement, that is how much restoring force is produced in the spring for a unit displacement in the block. Using Newton's second law of motion, F is equal to ma. So if we compare first and the second equation, we get A equal to minus k by m into x. As k is the spring constant, m is the mass of the block, both are constant values. So acceleration produced in the block is directly proportional to the displacement x, but negative sign is there, which is indicating that acceleration is proportional to the x displacement but directed opposite to it. This is obvious because displacement is increasing towards the right side, that is from A to B, but the restoring force, which is responsible for the acceleration, also is directed from B to A. So more the displacement x of the block, more will be the restoring force, greater will be the acceleration, but opposite to the in direction of increase of the value of x. So this equation, a proportional to negative of x, is the condition for checking whether the nature of a motion is simple harmonic or not. So for any motion we can prove this equation, that acceleration is directly proportional to displacement but directed opposite. That type of motion will be simple harmonic, otherwise it will not be. Differential equation of the simple harmonic motion. We know that from Hooke's law that restoring force is equal to minus k into x. Using second law, F is also equal to minus Fr is also equal to mass into acceleration. Comparing the two, ma is equal to minus kx. We know that acceleration is second time derivative of the displacement, so we can write this equation as d square x over dt square equal to minus k by m into x. If we substitute k by m equal to omega square, where omega is the angular frequency of the body, in that case we finally arrive at the equation d square x over dt square plus omega square x equal to 0. This equation is known as the differential equation of the simple harmonic motion with angular frequency omega. If we divide the unit of spring constant with the mass of the body, we get the unit of the square of the angular frequency. That's why the value of k by m is substituted equal to omega square. Time period of the simple harmonic motion, t is equal to 2 pi by omega. Time period of the simple harmonic motion is given by 2 pi by omega, as omega is equal to under root k by m. So finally we get time period t equal to 2 pi under root m by k. Or we can also write that for any simple harmonic motion of mechanical type system, time period is equal to 2 pi into square root of inertia factor divided by spring constant factor, because mass decides the inertia. Let us discuss about some basic definitions. Harmonic oscillator. A particle which is executing simple harmonic motion, we call it as a harmonic oscillator. Amplitude. Maximum displacement of a particle from its mean position, we call it as amplitude. Oscillation. One complete to and fro motion of a particle is called one complete oscillation. So if O is A is mean position, B is other extreme position, C is other extreme position. So if the motion is starting from point A, particle will first move from A to B, then it will move from B to A, then A to C, and when it will again come back to the point A, it will complete one oscillation. Time period. Time taken to complete one such oscillation is called time period, and the reciprocal of it, we call it as the frequency, which is the number of oscillation produced in 1 second. Angular frequency is given by 2 pi times the linear frequency, so that is omega is equal to 2 pi by t. Phase. At any instant of time, the phase of a particle gives its position and the direction of motion of the particle at that instant of time. So when particle is undergoing simple harmonic motion, it is moving from A to B, B to A to C, and then back. That is, it is sometime moving toward the positive x-axis and sometime towards the negative x-axis. So it is also changing direction. So what is the displacement or the position of the particle with respect to its starting point, that is A, and in which direction it is moving, that is indicated in terms of a physical quantity which is called as the phase of the particle.